What's a right angle?
90 degrees.
Which means, in layperson's language, what? An L? Yeah, okay, good. An L, or squared up. Now, when you start to have more than one right angle, if you have 3 lines, you will, of necessity, begin to have lines that are called what? What are those 2 lines to each other? Parallel lines. So when you start making right angles, you will necessarily create parallel lines. We've got 1, 2, 3 lines that are parallel, horizontal. 1, 2, 3, 4, 5 lines that are parallel, vertical. If they were perfectly parallel, that is, if they went infinitely in both directions, they would never touch each other. But what we want to talk about tonight is what they seem to do as soon as they go away from you. As soon as I take this chalkboard and go like that, parallel lines seem to do something. What was the term that we used last week to define? That they converge. Because of the principle of diminution, that is, things diminish as they go further away from you, or they seem to. They will come to a point somewhere. They'll get smaller and smaller until they meet at some point. And what do they call that point? The vanishing point, where they'll vanish. So the issue we've got to deal with tonight is that we've got these parallel lines that come from right angles that they will, as we tilt them away, diminish, appear to get smaller, and they will at some point where they will converge, come together at a vanishing point. Those are the things we're going to talk about. It's interesting what happens when beginners draw cubes. I know, I was a beginner, I drew cubes, had these same problems. That you kind of look at it and you try to compare angles, and you find that one of several things. One thing is that the lines, instead of converging as they're supposed to go away from you, will do the opposite. Okay? And when you're doing a rough, that doesn't make any difference. I mean, you might want to just put the position in there. When you start to refine it and make it accurate, it becomes important. See how those lines aren't converging? Another thing that beginners will often do is that lines will simply converge. They know they've got to get closer, so that one will converge like this, and this one will converge like this. So that one meets there, and these one meet over there, and they're just arbitrary convergence. It's not the way things work. There's a science to it that's specific. But to make it work, there's something you have to ask at the very beginning of the picture that you're going to make that has right angles in it. And it was brought up tonight. You have to ask, if that's the window that you're looking out into a world with, where am I? And the first thing you want to ask is, where am I as far as how high am I from the ground? It's called POV, point of view. You hear that word used in cinematography, and when you're storyboarding, you've got to determine your point of view. And the first thing we deal with that is height. You've got to find where your horizon line is. Now, in these perspective books that you're reading, they say that horizon line and eye level are the same thing. Has that ever confused you? Or has that ever kind of thrown you into my eye level and the horizon? I mean, they're as far apart from each other as any concept we're dealing with in making a picture, and yet my eye level and the horizon are the same thing? That is, if I move down, the whole horizon moves down. If I move up, the horizon moves up. That confused me for a long time, to say that if that's where the earth meets the sky, that's my eye level. And if that's where the earth or the ocean or whatever meets the sky, that's my eye level. There is a reason for it. This helped clear it up for me. Do you remember when you were a kid and you went for a ride in the car to Grandma and Grandpa's and there was a moon out? Do you remember that the moon followed you wherever you went? And it seemed like the moon was moving, and yet the moon is not the thing that's really moving like all those other things around you are. There's a reason this happens. If I have something close to me and I walk past it, do you see what happened? If I hold that in the same place, it's like it's in front of me, it's at the side, it went right back real fast. Somebody sitting in the back of the room, see, there was this kind of movement there. Somebody sitting in the back of the room when I take a step like that moves just a little bit. Somebody down the street moves infinitesimally. Something as far away as the moon, for practical purposes, it's at an infinite distance, right? Which means it doesn't move in my field of vision at all, which means if I walk 3 miles, it's always right there with me. Whereas the trees will go past me. But the moon seems to stay right there with me. The horizon does the same thing. Because your relationship to it doesn't change, it's always infinite. If I go up and down, boy, that fist really moved in relationship to my eyes, but the horizon line is going to stick right with it. Does that make sense? So that's how it was, that when you got home from Grandma and Grandpa's, the moon was still there at your home, and yet there it was at Grandma and Grandpa's, whereas all of the other things changed. So we say that eye level, how high I am, and horizon line are for practical purposes the same thing, even if you're working indoors. You have to be aware of what level is. Now, that tells you how high you are. That is, if you pull it down out of the picture plane, if it's down here, you're doing what? You're looking up at something. If your horizon line is up here, you've got vanishing points up there, you're probably going to be looking down at things. You're looking down at that park bench. So when you lift the eye level up, you're going up looking down on things. When you bring the eye level down, you're coming down looking up on things. But that only tells me about how high I am. It does not tell me about another thing that has to be dealt with, which is my relationship left to right, which is called a what? Anybody know? What do the books call that? A station point. You establish this station point, and you say, now I know where my height is, and I know vertically where that axis is. That's the station point. So let's do the old railroad analogy. It's a good one for making the point. There's the railroad track going back to the horizon. That's the vanishing point on the horizon. The vanishing point must be at a horizon. It's going to get more complicated than this, but I want to take it simply. We have to say, where is the railroad track? Well, the railroad track is right here in front of me, which means the ties on that railroad track are going to be what to my picture plane? They're parallel, yeah. They are parallel in reality. That is, if you look down on the railroad track, those ties look like this, do they not? Or actually, gosh, yeah, the rails have to go over the top of them or we'll have a little trouble. They are in reality parallel to each other, and in one point perspective, they look parallel to each other. What else might there be in here? Let's say that there might be let's put some people standing here. Let's have a person standing here next to the railroad track and another person standing here next to the railroad track. And we'll see that the major axis of their bodies, as they're standing up straight, they are vertical. Same thing would happen if you had a little building that was sitting around here somewhere. That would be, there would be now vertical lines. They are parallel. Those lines are parallel, and they appear parallel. But there is one set of lines that is parallel, still dealing with right angles, that appears to go away. It's the ones that are receding from my vision that will meet at one point. Now, that's a limited way to create space. It happens. Cynthia's desk is at 1 point perspective to me. Your desk is at 1 point perspective to me when I turn my head like this. But I can't turn my head enough to where Scott's desk will be in 1 point perspective. For 1 point perspective to happen, these right angles have to be lined up so that you've got a set that's going to stay horizontal to you, you've got a set that's vertical, and one set of parallel lines going away from you. Does that make sense? As soon as you step off that railroad track, what's going to start to happen? If those tracks are going away from you like this, they're still going to converge over there at the horizon line. We'll make our horizon line. Do you see how you're going to have the tracks going something like that? It has turned into 2 point perspective. As soon as you take this cube, which is sitting in front of you like so, and you turn it so that the corner faces you, now you've got a new set of lines that converge. Do the verticals converge? They are, in fact, parallel to each other on the cube, and they appear parallel to each other here because they're not going away from you. But now, this set that was horizontal is now going away from you, and they're going to converge somewhere. And the set going away from you to the right is going to converge somewhere. So you've got 2 vanishing points now. And that's why that is called 2 point perspective. Let's do a cube here. We'll put it on the horizon, or put it on the vanishing points on the horizon. Now, most of you know this from basic drawing. I'm going over it because I want to make it real clear, step at a time, what we're doing. 1 point is when you're looking right along something. That is, your face is parallel to a set of the lines. 2 point is when you tilt that thing, so now you've got 2 sets of parallel lines going away from you, and they will converge at a vanishing point. Now, this doesn't just apply to cubes. It applies to anything. Desks, tables, buildings, the lockers in the hall. Right? You can do a picture of the hallway where you're looking down the hallway, right? And you've got all sorts, you can have all sorts of things in there, but you're basically going to have a set of, let's line it up square for simplicity's sake. You're going to have a set of lines that recede from you, and you're going to have all these vertical lines of lockers. They're going to go to some arbitrary point, or actually it's not an arbitrary point, it's where your eye level is. But then, because I'm standing right there, if I turn, make this a different picture, so that I see, my vanishing point is going to be over here. I see these lockers over here like this. That means they're going off to that vanishing point, but if I swing a locker door open so that it's at right angles, forget about the arc that it makes. Let's swing one open. It means that those locker doors are going to have to come out something like this. Right? Now we've got a set of lines. That locker door is going to come out of there like that, and it's going to converge at a line on the horizon also. It turned into 2 point. When I was standing like that, it was 1 point. Turned into 2 point when I stepped into a different position. Now, does this make sense? And can you see that it applies to books? It applies to the street. It applies to that chair over there, even though that chair is going to have a number of complexities because it's got stuff like this going on, and it might have a curve like that going on, and a curve going on like that. Nevertheless, it's basically right angles. Okay, so now you understand 1 and 2 point. So what's such a big deal about 3 point? You know, the Renaissance artists didn't know or care about 3 point. When did 3 point come in? Anybody know? That's right. 3 point came in the 20th century. As far as I know no evidence of the study of it previous to that, because that's when skyscrapers came in, and airplanes and hot air balloons and helicopters. And so now we start to see things differently. And what you're doing with 3-point, remember 1-point, one set of lines converges because it goes away from you. 2-point, two sets are going away from you. One is staying the same, the vertical ones. So there we've got that basic 2-point. Now, if we decide that we want a worm's eye view or a bird's eye view, let's say a bird's eye view. We're up here looking down at that building, then you've got a reason to make this set of vertical lines converge, because you're in a helicopter looking down on that building. These are vertical lines. They're parallel, but they are going away from you, so they appear to converge. And likewise, you see your eye level's up here, right? Because these lines are going to converge somewhere on the horizon line. Remember, these have to do it too. And that's how you'd square that up. If you're doing a worm's eye view of the same kind of thing, you're going to have your eye level down there, and you're going to have this building going up like that. Horizon line will be down there. And what's going to happen? It's going to be another vanishing point up there for the sides of the building. Now you're looking up at that building. Okay, so that's why point of view is very important in illustration. For children's book illustrations, it's important because kids see the world regularly from this level. They look up at people's noses. They look under tables. They can get inside things like underneath the sink. And so when you draw for a kid, if you want empathy, you will draw from the kid's perspective, from the kid's height, point of view, which is a simple thing to do. You don't have to get down on the ground to do that necessarily. It might help so you can see that there's bubble gum underneath those things. But you just really need to put your horizon line at a point that a kid understands. Now, this applies to the cube, which could be a building, which could be a box, which could be the desk, which could also be, as George Bridgman made a big issue of, a human head. You can kind of sculpt a human head out of there, and you'll be able to look down on a human head and keep it consistent because you're thinking of the human head as a piece of architecture where you can see the planes. You'll see that that's going to fit into a cylinder down there, and the torso will be under there. And the same thing if you're looking up. You're going to have a box that you're looking up at. And if you can do that, then you can figure that a human head would fit into a box that you'd be looking up at. And you'd do the same thing. The ear would go there, the eyes would go somewhere in there. No, it's a specific. We'll get into that when we get into anatomy. I mean, Bridgman had a very specific proportion to the box, not a cube. Your head is deep and long, but not that wide. And you can tilt that cube in any position and find crucial points on it and put features on it. And they will have spatial integrity, which is a nice thing when you're doing anatomical studies, to give them that spatial integrity. And there's a secret to it. You think of things as simple shapes first, put them in any position you want, and then gradually get to the detail. And all that detail will conform to the big shape in the same way that every little window on this building, every little window, and not just every little window, but every little in and out on the window pane will conform to that vanishing point, or that vanishing point. Because it's all right angles. There may be some curves in there. We'll get to the curves. Now, here's the big secret. The big secret of understanding 1-point, 2-point, and 3-point. The big secret of understanding right angles that aren't just flat right angles, but right angles that exist in space, is that in 3 dimensions, in a 3-dimensional world, if you're dealing with right angles, there are only 3 sets of lines. Let me show you. Start out with the cube, which could be anything. Could be a human head, a book, a hallway, whatever. That's our one-point perspective. And let's go ahead and draw our horizon line so that we'll... If we could draw through that and see underneath that, as if it were made out of glass, it would look like that. There's only 3 sets of lines there. It's called one point because only one set of lines, the parallel lines that are going away from us, converge at that vanishing point. I've got to get those more accurate. They'd be more like that. That's how you square it up. This set of horizontal lines do not converge in our eyesight. This set of vertical lines do not converge. They stay vertical. They stay parallel. Okay. You've only got 3 sets there, the horizontal, the vertical, and the converging ones. Now, let's do a 2-point box. I'm not even going to bother to be sure it's a cube. It's just got to be a box. And we can do that thing as if it were made out of glass again. Oops. And that's where you can see where your errors lie. Two-point perspective, only 3 sets of lines. The first set of lines doesn't converge. Which set is that? The verticals. The verticals just stay parallel. But the set that goes away from us to the left converges at a vanishing point. And there's another set that used to be horizontal, but we've tilted it like that, and that set now goes away from us to the right and converges at a vanishing point. 2 of the sets of lines converge. 2 of the 3 sets converge, so it's 2-point. And now we'll do the same thing. I'm not going to bother to find those vanishing points there. Now we're going to look down on this box. And now there are all parallel lines on this, assuming it's something that's shaped in a right-angle box. But now all of the lines converge somewhere. 3 sets, all 3 of them converge. These ones off to the left somewhere, these ones off to the right. And this set that used to be vertical, down as they go away from us. Hence, 3-point. But the big secret is that if you're dealing with right angles that are consistent with each other, like streets tend to be, like the squares on this floor, and like these lights on the ceiling, you can pull that light down out of the ceiling, you can project things out at right angles, and there will always be 3 sets of lines, no more, until you start tipping the boxes around. Does this make sense? Here's the thing to remember, though. There's our railroad tracks. All right angles on those railroad tracks. Nothing but right angles. If we extend those rails and they're perfectly parallel and we extend them for several miles, you look down there at the horizon line and it seems like they touch somewhere. But you know what happens? If you walk, if somebody goes out there and plants a little flagpole and you walk to that flagpole, what will you do when you look down? Oh gosh, they didn't touch. And then you'll look out and you'll see another horizon line out there further where they touch. And it's like an oasis that's a mirage. It's just going to stay out there because in reality, these will never touch. This is something that's happening in your eyes because your eyes are lenses, because you're looking through a kind of window, and so it's an optical illusion. So when all these Renaissance artists started to analyze that optical illusion, they saw that there was a science to it, that it conforms to certain laws, and so because it conforms to certain laws, there are certain rules about how you use it, and this is it. That's the difference between 1, 2, and 3-point perspective. Any questions about it? Yes? Could I go over the last one again? You mean the 3-point one? You want me to make it more specific so I actually find the vanishing points? Okay. I've got to start over then. Actually, let me do one we're looking up at and one that we're looking down at. Let me make a new frame. Gosh, this thing makes it dirtier. Let's make our horizon line there. And let's make it so that we're